All right, so one thing we left out last time, we even had the question asked. I just forgot to answer it. We had the question asked, can you have an absolute minimum or absolute maximum that is not a local minimum or a local maximum? And the answer to that is yes, and it does come up in the homework. Okay? Because if we have one of the endpoints that is an absolute maximum or an absolute minimum, like on this one we got an absolute maximum at this right endpoint, it's not considered a local maximum also. Okay? I think the main idea on that is because we can't check values on both sides to call it a local. We've just got the one endpoint. So you can't have an absolute maximum and it not be a local maximum if it's at an endpoint. Okay? If you have something on the interior of the interval, if we have an absolute maximum, like if this was up higher, it could be an absolute and a local, but it's possible it's one and not the other. Okay? I thought about that as soon as class was over, that I forgot to answer that. Okay. All right. Other questions on that assignment? Yep, so critical numbers. Take the derivative, set the derivative equal to 0, and solve for x. That'll give you the places where the derivative is 0. Then you also need to check to see if there's anywhere that the derivative would not exist. So typically that happens when you would have an undefined situation. So if you have some x value that's not in the domain of the derivative. So two things make a critical number, where the derivative equals 0 or where the derivative does not exist. Does that help? Okay. See anything else? All right. Okie dokie. Well, let's look at 4.2. My voice is in and out today because of the crazy weather change. So sorry, I got a peppermint in my mouth. I apologize for that, but it helps me be able to talk. So what we need. This assignment will not be due until after spring break. It's kind of silly to wait until after spring break to do it, but I'm putting the due date due the Monday after spring break, because I typically try to give you a week after we cover a class, and that's the Monday of spring break. I'm not going to do that, so it'll be the Monday after that. But this assignment's pretty short, and we've only got one other one due this week, so I would go ahead and try to knock this one out before spring break if it was me, and then you don't have something due on the first day when we come back. But if something happens and you need the extra time, it's there. So in this section, we're getting ready for the rest of the chapter. In this section, we really just have two theorems we're going to look at. And then we're going to just kind of practice applying the two theorems. And then that'll get us set up for the next section. So Wednesday and Friday, we'll work on 4.3, and that'll be where we stop for spring break. But we need this section really to get into that stuff. So we've got two theorems we're going to take a look at. You're not going to have to prove these or anything, but you will need to be able to apply them. And you need to be able to check the conditions, those kinds of things. So our goal, okay, is to get to this thing called the mean value theorem. But to do that, we have to go through this other theorem called Rolle's theorem. And Rolle's theorem, we have three conditions. It says that if we have a function that satisfies the following three hypotheses, so three things we need to check. Okay. Number one says our function is continuous on some closed interval a to b. Remember, closed means it includes the endpoints. We write that with the brackets. We need our function to be differentiable on the open interval a to b, so we're not having to worry about the endpoints there. And then number 3 says f of a needs to equal f of b. So what that's saying is that if we take the left endpoint and evaluate our function there, take the right endpoint and evaluate our function there, we get the same value, we get the same number. Okay. If we have those 3 things, and then here's our payoff. Here. It says we're guaranteed in that case that there's some number in that interval a to b, and we're calling it c, where the value of our derivative at that number will be 0. So it's guaranteeing us that there's some x value in this interval where our derivative at that x value will be 0. So 3 things. Got to be continuous on the closed interval, differentiable on the open interval, and the endpoints have to give us the same value. The endpoints have to be equal y values. Then we're guaranteed there's a number in there where our derivative at that number is 0. Okay? So we can come back to this if we need to, but here are some functions that satisfy those conditions. Okay? So we could have a constant function. Then for sure the endpoints are equal. Right, that makes that part easy. If we have a constant that's continuous everywhere, we just got a solid horizontal line, right? So it's going to be continuous on the interval. It's differentiable everywhere, it's just flat. Ain't nothing interesting going on, so it's differentiable on the open interval. The endpoints are equal, so we're guaranteed there's some number in here where if we find the derivative at that number, it's going to be 0, or in other words, at that x value, if we find the derivative, it's going to be horizontal, right? Or horizontal tangent line. And that's pretty obvious on this one because the whole thing's a horizontal line. So no matter what x value we pick, we're going to have a horizontal tangent line. Okay. B is a little more interesting. Okay. Nice and smooth, so we can tell it's continuous on the closed interval. We don't have a cusp or a corner or anything, so we can tell that it's differentiable on the open interval. So we're guaranteed there's at least one number in here, and it happens to be right here, where if we find the derivative, our derivative is going to be 0, and we can tell that because we have a horizontal tangent line. Okay. We can have more than one. This one, you check the 3 conditions, we're good. Here we've got 2 x values where we have horizontal tangent lines. That's okay. We can have more than one. We're guaranteed that we have at least one, so we can have more than one. Okay. And here's another one. These are just basically opposites of each other. Okay. So that's what Rolle's theorem is saying. Okay. It's saying that if our function is continuous, differentiable, and the endpoints are at the same y value, the only way that can happen is if we've got at least one number in here where we have a horizontal tangent line. And if you think through that intuitively, it's going to seem pretty plausible because, like, if we start off with our function going up, the only way we can get back down to this level so that our endpoints match is for us to turn around. And when we turn around, we get a horizontal tangent line. Same thing if we dip down, we've got to turn around and go back up so our endpoints stay the same. So when we turn around there, we get a horizontal tangent line. Okay. Or, if we stay the same level the whole graph, then that works too. Okay. That's Rolle's theorem. Okay. We're not going to prove it. Okay. You can save that for another day. That's what Rolle's theorem is telling us. Okay. You got the conditions? That's the main thing there. Be continuous on the closed interval, differentiable on the open interval, the endpoints have to be equal. And we've got this guarantee we've got a horizontal tangent line somewhere in that interval, or that our derivative equals 0 at some x value in there. Questions? Okay. All right, so got Rolle's theorem. That's not the one we really want. Rolle's theorem is useful. The main thing we're going to use Rolle's theorem for is to give us our next theorem. The next theorem called the mean value theorem. Okay. Mean value theorem is really important. It comes up a lot proving different calculus topics. Okay. Again, we've got some conditions. Okay. Here we've got two. The first condition we need our function to be continuous on the closed interval, a to b. Number two, we need our function to be differentiable on the open interval, a to b. We're not worried about the endpoints being equal on this one. We don't care. If the endpoints are equal, it just turns into Rolle's theorem. Okay. So the mean value theorem is really for the situation where our endpoints don't match. In that case, we're guaranteed that this is a little more complicated to digest, and that we've got a number in our interval so that the derivative at that number is this thing, f of b minus f of a over b minus a, or we could write it this way, that f of b minus f of a is f prime of that number times b minus a. Let's look at what those two things are telling us. This is a slope somewhere, right? Like y2 minus y1 over x2 minus x1. Just label it a little different. What's that the slope of? Where are a and b coming from? A and b are the endpoints of our interval. Okay. So what this is saying is that if we've got some function and we're thinking about it starting at a and it ending at b, okay, this slope, f of b minus f of a over b minus a, that's the slope of the secant line between b and a. Okay. That's what that's saying. So backing up a little bit, it says if we've got these conditions, there's at least one number in our interval so that the derivative at that number is the same as the slope of the secant line between the two endpoints. Okay. Equation number 2 down here says the same thing. It's just, we're just multiplying both sides by b minus a. This is in the form. This is like y minus y1 equals m times x minus x1. So this one's written like this one's saying this slope is this, and this one's saying we've got this line that exists. Okay. So the same thing. Okay. All right, so let's look at a picture. Okay. So here, our black curve, we've got a function. It's continuous on the interval a to b. No holes, jumps, or vertical asymptotes. It's differentiable on A to B. No corners or cusp or discontinuities. And we don't care if the endpoints are equal anymore. We don't care if they're horizontal. What we're saying is that there's at least some point in our interval, C on this one, where the slope of our tangent line at C is the same thing as the slope of the secant line between the endpoints. Okay? So you can tell this line's parallel to this one. So that's what our mean value theorem is guaranteeing us, is that there's some number in here where the tangent line is parallel to the secant line between the endpoints. Even if you have something with more turns, okay, same thing's true, and you may have more than one place, more than one x value where you get that parallel tangent line. Okay. Here we've got 2. Okay. So at C1, they're calling it, our tangent line is parallel to the secant line between the endpoints. And then at C2, our tangent line is also parallel to the secant line between the endpoints. Okay. And that doesn't seem all that impressive, maybe. Okay. But if you, it's really nice, okay, because we can guarantee that those tangent lines exist. Okay. So that turns out to be important. But it's also really nice in application. So let's back up and talk about this as like rate of change instead of slope. Okay. So the mean value theorem says if we have these conditions, then there's at least one number in our interval where the instantaneous rate of change is the same thing as, well, this would be the average rate of change from the beginning to the end of our interval. Okay. So that's nice. So what that's saying is if we can figure out the average rate of change, there's somewhere in our interval where the instantaneous rate of change is that same number, or that same slope, the same rate of change. Okay. So the example that gets used a lot only is to try to apply it to daily life. Okay. Let's think about this. Okay. All right, so let me adjust my pen here. Here's cop number 1. Here's cop number 2. Okay. Here's your car. You're driving fast, so you got a red sports car. I know that looks like a red sports car too. Okay. You're driving this way. Okay. Cop number 1 get you going 68 miles an hour. Okay. And you go by cop number 2, get you going 67 miles an hour. We're in a 70 mile per hour zone. So you're good, right? Neither one of them caught you speeding. Right? Yeah, you saw them, you slowed down. Okay, so you're safe. Not necessarily. And not necessarily. Because what you didn't know, cop number 1 started a timer when he clocked you. Cop number 2 stopped the timer when you got there. So they can figure out your average rate of speed. They know how far apart they are. Maybe they're like a mile apart to make it easy. Okay, so they can calculate your average rate of speed between the 2 points. Okay. So when they calculate your average rate of speed, they got 73 mile per hour average. What's that mean? Mean value theorem. if your rate of change, average rate of change between the endpoints at COP 1 and COP 2 is 73 miles an hour, then there's at least one point in the interval between COP 1 and COP 2 where you were driving how fast? 73 miles an hour. Okay? You can get a ticket, even though they got you going 68 and 67. Okay? They can pull out some calculus and write you a ticket. Write you a ticket. So that's because we know there's somewhere in there where your instantaneous rate, your instantaneous velocity was 73 miles an hour. Probably higher than that, right? But that's what's going on here. Ever thought about that? Did you know they could get you like that? I don't know if it would hold up in court, but they could get you. You could, not legal defense, but you could probably say, well, I stopped at a gas station and somebody else drove from here, and then I ran down the road and caught them and started driving again there. So you weren't driving the whole time, so that's what I would say. Okay? Can't get you. They'd have to prove you were driving the whole time. So, okay. All right. So that's the mean value theorem in driving terms. Okay. Let's look at some math application here. Okay. This is a short assignment. Okay, we're just applying the Rolle's theorem and the mean value theorem a couple of different ways. But we're going to use this thing a lot. We're going to depend on it for some of the things we're going to do later, so we want to get a little familiar with it. Okay. So let's look at this one. Okay. It says let's look at the mean value theorem for a specific function. So we've got x cubed minus x, and then our endpoints are 0 and 2. Okay. To me, it's kind of hard to follow how the textbook walks through this, so let's walk through it on our own and see if we can't do better. Okay, so we've got x cubed minus x. And then the interval we're concerned with is 0 to 2. Okay. We want to check out the mean value theorem here. Okay. So first we need to check our conditions. Okay. Mean value theorem has 2. All right, Rolle's theorem has 3 because with Rolle's theorem we also want the endpoints to have the same value. Mean value theorem, we only care about the first 2. Okay. So first we want our function to be continuous on the closed interval 0 to 2 in this case. So is that true here? How can we know? What kind of function is that? What family would you put it in? Polynomial. I think we've had some theorems about polynomials. We know where polynomials are continuous. Where are polynomials continuous? What x values? All of them. Okay. So polynomials are continuous on the whole number line. Okay. So I'm going to say f of x continuous from negative infinity to infinity. So it's continuous on 0 to 2. Okay. We need our function to be differentiable on the open interval 0 to 2. Okay. Where are polynomials differentiable? Remember that one? Do polynomials have any corners, or do they have any cusp? And they don't have any discontinuities. So polynomials are continuous, are differentiable everywhere. So the differentiable everywhere, it's differentiable on 0 to 2. Okay. So now what the mean value theorem tells us, okay, is there is some c value in the interval 0 to 2 such that, well, we had two ways we could write it down. This is a prime here. I know it's hard to see. Doesn't show it real well sometimes. Either f prime of c is this, or we can write this statement down. On this one, I think it's going to be more convenient to look at it this way. So f prime of c but f of b minus f of a. So that's our endpoints, right? So f of 2 minus f of 0 over 2 minus 0. That's f of b minus f of a over b minus a. Okay. This thing we can actually calculate. Right. F of 2 is 2 cubed minus 2. That's 6. F of 0 is 0 cubed minus 0. That's 0. And so we're plugging up here. 6 minus 0 over 2 minus 0. That's 3. Mm-hmm. Okay. With me so far? Okay. All right, now what we would really like to do is to figure out what C is. Well, figure out where that happens. Okay. One second. Yeah, okay, sorry. I'm blaming it on time change. Okay. Because we know what, so we know what? We know f prime of c, 3. Okay. What else can we figure out? We've got f. What can we figure out from f? We can take the derivative. and take the derivative. So if f of x is x cubed minus x, I'm just copying that down. And what's f prime of x? 3x squared minus 1. So what would f prime of c be? We just plug in for x. 3c squared minus 1. But also, what do we say f prime of c was? 3. So this has got to be 3. So 3c squared minus 1 got to be 3. Three c squared, add 1 to both sides, you get 4. C squared is 4 over 3. This one's a little bit ugly. So c is plus or minus square root of 4 over 3, which is plus or minus 2 over root 3. That sometimes they come out nicer. Almost done. One of these does not apply because what's our interval? 0 to 2. So which one of these do we not care about? Yeah, the negative 2 over 3, or negative 2 over root 3. I can get rid of that one. So our c value in this interval (2 over root 3). 2 over root 3. Okay. Let's look at the graph. Look at what we're doing. Okay. Here's our function. Minus, yeah. There's our graph. We only care about the part between 0 and 2. All right, and our endpoint's way up there, so we're caring about our interval from here. Here's our left endpoint. There. There's our right endpoint. We're saying somewhere along this curve between 0 and 2, our tangent line has the same slope as the secant line between the two endpoints. And we just said, where does that happen at? That happens at the point 2 over root 3 is our x coordinate. So, not 0. Let's see where the point is at. That's our c value, so if we plugged it in, that's going to be something ugly. We'll come back when we get a nicer one, but 2 over root 3, well, that's decimal. We can approximate it here. A little bit bigger than 1. That's saying somewhere in here, our tangent line is going to be the same as the secant line slope through parallel. Sorry that I'm ugly on that one. We'll find another one here in a second. Switching on any of that part. All I did was plugged in, using my endpoints. So the theorem says f prime of c is f of b minus f of a over b minus a. All that we can find because our left endpoint's a, right endpoint's b. We can figure out what f of c should be. And we can also find f of c by taking the derivative and plugging in c for x. Then we just solve. Find those c values, but you do need to check for the ones that are in the interval. Maybe I've got a better example here in a second. So then else we can do with this. Oh yeah, there's a picture. Forgot they had that graph in there. Let's look at something else. This is not super obvious that we can do this. So it says suppose that f of 0 is negative 3. So our function value at 0 is negative 3. And f prime of x is less than or equal to 5 for all values of x. How large can f of 2 possibly be? So all we know a function value at 0. And we know that our derivatives have got to be less than or equal to 5 everywhere. And we want to put a bound on how big f of 2 can be. Okay. So what we're doing here, we're going to take the mean value theorem, okay, and use the interval 0 to 2. Because we're looking at f of 0 over there. We're looking at f of 2 here. And so we can just make that our interval 0 to 2. Okay. And that guarantees us this. Okay, that exists because that function is continuous on the interval and it's differentiable on the open interval. Okay, so that guarantees us that. Okay. So let me just copy down what they've got there because the textbook version gets a little harder to follow than it needs to be. Okay. So we've got this. We've got that f of 0 is negative 3. And f prime of x less than or equal to 5 for all x values. We want to know how large can f of 2 be. So if we take the interval 0 to 2, apply the mean value theorem, then they've given us this part. That's the version of mean value theorem that looks like the point slope form. Right? It's like y minus y1 equals m times x minus x1. That's the one they call equation 2. Okay. All right. What do we know? What can we do here? We're just going to start working some algebra. f of 0 is negative 3. Is there anything we can do on the right side? 2 minus 0 is just 2. 2 times f prime of c is just 2 times f prime of c. Right. We're trying to figure out how large f of 2 can be. So let's get it by itself. So f of 2, again, subtract 3 from both sides, right? Minus and negative 3 is plus 3, so we got 2f prime of c minus 3. What do we know about f prime of c? It has to be something. We've got a condition on it. Got to be less than or equal to 5 because f prime of x is less than or equal to 5 for any x. Okay. So a little bit of side work here. Well, if f prime of c less than or equal to 5, we've got 2f prime of c, so we can multiply both sides by 2. 2f prime of c got to be less than or equal to 10. So it'll be less than or equal to 10, the 2f prime of c part does. We're taking away 3 here, so we can take away 3 there. So what do we know about f of 2? F of 2 has got to be less than or equal to 7. Yeah, 7. Because f prime of c is less than or equal to 5, we know that. But we're talking about the endpoint here. So f of 2, not f prime. F of 2 has got to be less than or equal to 7. Maybe we could have done that in a different order when I back up. Let's leave the plus 3 over here first. Maybe it'll be a little bit easier to. Okay, I got that. We know 2f prime of c has got to be less than or equal to 10. So f of 2 plus 3 equals 2f prime of c. That's got to be less than or equal to 10. And then we can subtract 3 from everywhere. Nope, minus 3. Then even better to follow. Or worse. I know when you get to Cal 1, you haven't had to do a ton of inequalities. So. Hanging in there. Hang on, we'll do a couple more examples and it's not as bad as it seems, I promise. We get a theorem and a corollary from the mean value theorem just very directly. Okay. Our theorem says if f prime of x equals 0 for all x in the interval, then it means f is constant on that interval. And then if the slope of the tangent line is 0 on the whole interval, it's got to be constant, that horizontal line. And well, not quite so obvious. It says if we have two derivatives that are equal to each other for all x in an interval, then if we subtract two functions, it's got to be constant. It's got to be constant. It's easier to think about it here. So let's rewrite that. We subtract g of x from both sides. Let's say in this. So the difference of the two functions got to be constant. Okay. And that geometrically, maybe that's easier to think about. That's saying that the derivatives are the same for two functions. So like if that's f and that's g, it's not my best drawing. Get the idea. If their derivatives are the same, that's kind of what we're saying is we're talking about an idea that kind of like parallel. The parallel, we're talking about straight lines. What we're saying is one graph is just a translation of the other. So like if we move this one up, it would match up. That's the only way we can have two functions where their derivatives are the same over an interval. What that means is if we subtract, the only thing we're left with is how much is shifted by the constant. Don't fret over that. Let's do maybe some better problems. Look at this. Here's a function. And we're going to think about the interval 0 to 2. Okay. Okay. Well, one thing about the mean value theorem here, so does the mean value theorem apply? Got two things we got to check. Got to check that the function is continuous on the closed interval, that it's differentiable on the open interval. What kind of function is this one again? Polynomial, so yes, that makes that easy. Okay. Polynomial function, so that it's continuous everywhere. It's going to be differentiable on the open interval, no problem. Okay. So the mean value theorem does apply. Okay. And then part 2, this is one just like in the homework. Okay. Says if it satisfies the mean value theorem conditions, find all the C's that satisfy the conclusion to the mean value theorem. So what we're wanting to do, we want to find all C values such that f prime of C equals f of B minus f of A over B minus A. What's our B value on this one? 2, yeah, it's going to be our right endpoint. our A value is 0. What we want, in our specific instance, we want f of 2 minus f of 0 over 2 minus 0. Okay. F of 2, we plug in. So let's see, 2 squared is 4. 4 times 4 is 16. Minus 5 times 2, so that's minus 10. Plus 1. So f of 2 is 7. What's f of 0? It's a little bit easier. 1, yeah, 1. So we want f prime of c equal 3 again. Is this the same problem we did? No, it's different, isn't it? Right, equal 3. Okay. All right, so we know f prime of c, it's got to be 3. I promise it's not always 3. Okay. You get f prime of c, we can find f prime of x. What's our derivative going to be? 8x minus 5. So if that's the case, f prime of c would be 8c minus 5. So we know f prime of c is 3. So we need 3 to be 8c minus 5. Add 5 to both sides. Get 8 equals 8c, so c is 1. C is 1. We'll have 1 this time. And 1 is in our interval 0 to 2. Okay, so that one works. That one works. You can't have more than 1, but the mean value theorem guarantees us at least 1 c value. So that's true. Was that one a little better? Another one. Okay. You can do the same thing with Rolle's theorem. You just do it exactly the same way, except the only thing different is that if Rolle's theorem applies, the endpoints are equal. So this thing just turns into 0 because f of b minus f of a is 0 over b minus a. So you get f prime of c equals 0. Then you find the derivative and find the derivative at c. So you'll have this equals 0. You can do Rolle's theorem then. Okay. So you do some of them. Let's see, 1, 3 say do mean value theorem. 2 say do Rolle's theorem, find the c values. Okay. And then there's 1 like that last one we did. Okay. So let's see. Let's do it. Get another example in. So to do these, we need to use the mean value theorem. We need to know what interval we're doing it on. Remember how to set that up? We want to do it on the interval from, it says f of 1, so we're going to start at 1. And we want to know how small f of 4 can be. And so that number, that number, that number, that number. Okay. So then, the mean value theorem. Okay. Okay. What do we know then? Okay. We know f of 4 minus f of 1 equals f prime of c is 4 minus 1. That's just that equation 2 form of the mean value theorem, plugging in a and b. Okay. What do we know? We know f of 1 is 11. And on this side, 4 minus 1 is 3. Okay. So f of 4 minus 11 equals 3 times f prime of c. Get the 3 here, and then 3 times f prime of c. And what do we know about f prime of c? F prime of c has got to be greater than or equal to 3. So if you want to, you can do scratch work. So we need 3, so we can multiply both sides by 3. So 3 times f prime of c has got to be greater than or equal to 9. And then at 11, we want to solve it for f of 4. So 3f prime of c got to be greater than or equal to, no, plus 11, sorry. Got to be greater than or equal to 9 plus 11, which is 20. So what's the smallest f of 4 can be? F of 4 is greater than or equal to 20, so the smallest it can be 20. Yeah. 20. You only got one of those today. There's only 6 problems. Only 6 problems. Okay. That's it. Not a lot of we don't have a lot of calculations and stuff we can do with that, but just trying to kind of get a feel for the theorems because we're going to use them quite a bit.